Okay, so the first problem we want to try today that involves impulse is given by this statement. I throw a rock or a tennis ball against the door to close it. Which would be most effective if they have the same mass? Okay. So what we can do then is grab the pink sheet and note that I have a collision. It does not create any rotation. Is it time dependent? Let's say no. And then, are there initial and final picks? Yes. So we can use conservation of momentum to figure this out. But one of the issues we have is that the collision with the door, that collision isn't well quantified. So we're going to have to really use the full conservation of momentum term. So let me show you what that looks like. All right, let me make sure we're squared. Okay. So in parsing, what we would do is we would say draw a rock, and then this is its initial picture, and that's our door. Our final picture has the door on its hinge, the rock which previously had a velocity because I've thrown it, now has no velocity because it's a rock. When it hits things, it smacks and drops. This is the same for the ball, except for the tennis ball is going to bounce back. So let's do the ball case over here. So going to hit the door. The ball comes in with a velocity. This is initial. Then the ball hits the door again. Well, it's hit the door. But when a tennis ball hits the door, it bounces back. Notice that over here I need to have the velocity final and the velocity final for the ball case as well. My question was, most effective? Kind of a poorly defined question. So we'll add the phrase closing the door. The big concept here is going to be momentum. So step one, let's do the rock. And we'll keep this representations and stuff pretty straightforward at this point because we're in one dimension. So we'll do final and initial. And I've got the rock, so I'm going to have a rock and a door. Rock and door is my system. Initially, same thing. Rock, door. So initially the rock has all the momentum. And in the final case, the door has all of the momentum. Let's contrast that with the ball and door system. Need to make sure we're still there. There we go. Sorry about that. So what I was talking about down here is I chose the rock and door system. So I put my rock and my door in my system line, and I give the door its momentum after the collision, and the rock has all of the momentum before the collision, because we are assuming that delta P is equal to 0. If we do the ball and door system, we'll get a slightly different outcome, which might be enough for us to answer the question. Okay, so in the final case, I've got the ball and the door, and initially I've got the ball and the door. So initially the ball is carrying all of the momentum. However, at the end, the ball has bounced back. So that means the ball is going the opposite direction. Momentum can be negative, since it's just mass times velocity. So what we can see then is if I do my total momentum, so change in momentum should be 0. I have 2 objects in my system. The momentum of the rock plus the momentum of the door, and that has to equal the momentum of the rock and door again, only in this case it's final and it's initial. Again, the best thing about solving a physics problem is that you hunt for zeros as quickly as you can, and we can get that from the bar chart. So final, the momentum of the rock has dropped to 0. The door has a momentum. The rock has a momentum initially, but the door does not have a momentum initially. So what we wind up with then is that the momentum of the door is just equal to the momentum of the rock, which has its mass and has its velocity. This is going to be slightly different when we come over here to the approach for the ball. Our equation is delta P is equal to 0. So I can put P initial on one side, so P of the ball plus momentum of the door that has to equal the momentum of the ball plus the momentum of the door. And again, this is the initial case, and this is for the final case. So we look at the final case, and I didn't draw anything for the door because I didn't want to give away this really cool effect. So the momentum of the ball, assuming it bounces perfectly, so let's make that assumption. Then in the final case, the ball has its mass for its momentum, but is carrying a negative velocity. And then we're going to have the momentum of the door. That has to equal the momentum of the ball, its mass times its velocity, plus the momentum of the door, which in this case really is 0. It starts from rest. So watch what happens to the final momentum of the door. I have the mv from the initial plus an mv from the final. So I basically wind up getting 2mv for the momentum of the door, which answers our question that what I have to do now is take a quick look at the evaluate and say, look, I've got two equations. I know that P door is equal to mv for the rock. That should be P door final. And that the momentum of the door final is equal to 2 mv of the ball. And that's what we need. So now we have to answer the question. The tennis ball is most effective. Checking our units is sort of trivial since momentum is defined to be mass times velocity, and that's what we have in both cases. So momentum has units of kilograms, meter second, and momentum doesn't have a name. There's no petty little calling it a Newton or a joule or something else. It's just kilogram meter second, which is given over here as kilograms times velocity, meters per second. So our units check. Is the answer reasonable? Even without numbers? I would actually say it's surprising, but it's I'm going to say surprising, but cool effect. What's nice about this problem, where you have something hitting another thing versus something hitting something that bounces off, is this is how solar sails work in space, where photons come in, and if you have a silver solar sail, those photons will bounce back, producing a final velocity for the door, which is twice as effective as if you had a standard black sail. Okay. So I will call this momentum 1 and try to get it scanned and posted sometime for you to look at the whole sheet.